Hi, I'm Barber from the University of Lincoln, and today I'll be talking to you about the effects of weight pruning on a sequence-to-point learning-based approach to energy disaggregation. Previous work has shown that this approach to disaggregation works well and trained models are capable of providing good results. However, the neural network strains contain upwards of 30 million weights, which makes inference slow on consumer-grade computing devices. The implementation works by taking in a sliding window of 599 aggregated power values and attempts to infer the disaggregated value at the midpoint of the sliding window. The network contains 5 convolutional layers with an increase in number of filters the further into the network you get, with a fully connected layer containing 1024 weights. Our solution to the large number of weights in these models is weight pruning, which is the process of setting non-essential weights in a network to be equal to 0, which in turn reduces the number of calculations that need to be performed during the forward propagation process. This theoretically makes the inference times of the model faster. Our methodology involved taking 4 pre-existing pruning algorithms, including TensorFlow's low-magnitude pruning algorithm, a structured probabilistic pruning algorithm, a relative threshold pruning algorithm, and an entropy-based pruning algorithm, and producing 2 models per pruning algorithm, one trained using the kettle portion of the refit dataset and the other using a dishwasher. The best performing algorithm would then be used to train a reduced network architecture with fewer weights in the hidden layer and fewer filters per convolutional layer. We also applied dropout to this. At first glance, it looks as though the structural probabilistic pruning algorithm performed best, as it yielded the lowest errors when trained to disaggregate the cattle appliance. However, it only removed a negligible number of weights versus the control model, as it only removes weights from the convolutional layers of the network. After analysing our results, we came to the conclusion that the low magnitude pruning algorithm performed the best, as it removed over 2/3 of the weights whilst also only suffering a 2% degradation in error. After applying this algorithm onto a model trained using the alternative architecture and dropout, we managed to create a model that contained 12% the number of weights compared to the control model, whilst also decreasing the errors significantly. Here are some of the sample plots produced by each of the pruning algorithms, where the green line shows the inferred disaggregated energy value, and the orange line shows the true disaggregated energy value. You can see that the SPP algorithm produced a sample plot that was close to the true value, whilst the low magnitude pruning algorithm both under and overestimated the values throughout the window, but over the span of the plot it averaged out to be reasonably close to the true value. Whilst I appreciate this has been a rather fast overview of our work, please feel free to contact me if you have any questions and I'll be more than willing to help.